Hi guys, welcome back to the Astro Imaging channel. Tonight's session, Statistics in Astrophotography, and it's going to be presented by Alex McConaughey. But as always, before we go into that, I am going to show off our image of the week, which goes to, excuse me, gotta hide that, Diego Colanello, who's won a few of these, but this is a unique object, at least to some of us Northerners. This is the Tarantula Nebula, and he had shot this from the Vic South Star Party. And of course, like I said, Tarantula Nebula NGC 2070, Skywatcher 10-inch f4 with a ZWO optical ASI 1600. Very nice job on this image. And one of those targets that a lot of us would like the opportunity to shoot, but we have to do some traveling for it. Thanks for submitting, and as always, guys, you could submit on our website, and maybe we'll be showing off your image next week. That said, I am going to take my screen back and hand it directly over to Alex. There you go, Alex. You are on. But you are still muted.
I'm still muted. Okay. Okay. Hi, everybody. Let's go back to screen sharing here. Okay, you got the screen showing properly now? I think you do. Yes. Okay, yes. We're going to be talking about statistics for imaging. It's not a full-blown statistics course. It's just enough to help you understand a few of the things we do in imaging. And one of the things that happens when we're imaging is we get into this argument about whether it's our astro images are art or science. And we had a couple of discussions about this recently, about the ethics and things like that. And frankly, it's neither art nor science. Visual art, for instance, is color, shape, and form, and actually an astro image contains no color or shape or form even. It only contains a bunch of numbers, and that's pretty important to know because it's manipulating those numbers that gives us everything else we want. And manipulation of numbers is called statistics. Not exactly mathematics. It's a sub-branch of mathematics, perhaps, which tries to get some meaning out of the mathematics. Now, here's a chart, and it's pretty easy to understand chart, and it covers some of the major points that one's going to make about statistics. And with statistics, what you're trying to do is you have a bunch of numbers, and you're trying to figure out how they're distributed. You're trying to figure out what the range of those numbers are, what the variation among those numbers are, what the center of the number is, and basically the shape of how they're kind of distributed. And that's the important things for an astro imager. You're also probably trying to figure out with statistics the correlation of one set of variables with another set of variables, the dependent and the independent variables. And in order to do that, you've got to be able to analyze your numbers in a way that makes sense, and you can convince others that you've actually analyzed the numbers. By range, it's very simple. We mean the distance from the lowest member of a set to the highest number of the set. And in the dark blue distribution of the data here, you see that that's a pretty wide spread compared to the red especially, which goes from 60 to 120. Well, boy, there's a whole lot of tail ends on either of the distributions here. So you can tell that this is a different data set, the blue one. It's a lot noisier. It's a lot harder to predict anything from it. Where if you had the red data set, you'd know that pretty much everything is right in the middle. Both of them happen to have an average of 100. But the standard deviation, how far you typically are away from that average, is only 10 if you're the red people, but if you're the blue people, it could be as high as 50. All right, so that these are all the shapes of these things, the kurtosis of the lines and things, they all mean something to a statistician. We don't need to know all of it. We just need enough to know, make a sense of some of our numbers. Now, I said earlier that there is no color, shape, or form. There's only numbers. And just to make sure that you understand that there is only numbers, our images are really just places on a grid with values. And that grid, depending on the size of your sensor, here's one with 0 up to 25 in the rows and zeros down to 14 in the column. So we have each space on this grid has a corresponding name, and it's named after its column and its row. And so that's space number 13.7, that's space number 713, there's 2514. And what's happening is we go on out on a cold night, hopefully, we'll get on a clear night and we'll gather photons. And for the number of photons that hit this particular square or this particular square, we'll count them all up. And then we'll come home and we'll figure out what all those numbers mean. And we figure out what all those means according to our statistics. The more photons that fall on any given square, the higher number we assign to that square. And we assume that that means it's a brighter part of the image. So when we're finished, we get something that looks about like this. We got our rows, we got our columns all the way across, and we got numbers. We got lots of numbers. We got so many numbers that we've got to file them away someplace. And I've jumped ahead too far. So I should point out something to you here, though. But you know that this gridiron is strictly rectangular. There's no such thing as a round pixel. There's no such thing as a star-shaped pixel. They're not. Everything is a square. Celestial objects, however, are not. If we take a star, we'll find out that that star, there are places where it completely misses, places where the star completely misses filling in any of the squares. But there are other places where it completely fills in the square. And there are places where it only partially fills in the square. And of course, we're talking about a star, this artificial star I've drawn here, that's the same brightness all the way across from each tip to every other tip of its 5 points. What happens here? You can see that the light is only covering half of this particular pixel. So it can only gather about half as much light as the light can come in here. Hey, and tell me about what's happening up here. This is white. How could that possibly be white? Nothing around it is white. Do we have a little star that's so small, yet so bright it can fill all that up and not spill off into any of the other sides? Well, the grid is strictly rectangular and celestial objects are not. When we put that star on top of our grid, we'll find out that the parts that are up in the very corner don't get nearly as much light. And if the pattern of the light comes down across here, some pixels will only get a partial collection of that light. Now, amazingly, when you assign light values, white values to each of those little numbers, you find out that you get something that kind of looks like a star. And obviously, this is a very blown up grid in the middle here, but you can see that as we shrink it down further, hey, look, it almost looks like a star. Okay, that's because the grayish parts kind of drop off and the whitish parts get brighter and things like that. But we still have these defective pixels. See this one here and this one up here? It's still up there. So that's something we got to worry about. We got to take care of that stuff eventually. Now you can actually see these grid pixel values in most of your word processor or most of your image processing software. You call it up and you put your cursor on top of a bright point and you're going to get a couple of things. So you can see it down here in the bottom. This is a PixInsight, but it goes on almost any other piece of software. I'm at position, well, let's make that bigger so you can see it. This is basically repeating what's down here further. But that little cursor is on position 131, 315, meaning it's 131 columns across and 315 rows down. And I can also tell, because I told it to tell me this, what the color saturation value of this, or what the, I'm sorry, not the color saturation, but the light value is of this, and it's got a value of 3,636. If I move that cursor right now, it's that particular pixel, and when it's really blown up big, you can see it like that. It's at exactly position 131.53, and like that. But I can move it from here up to here, and I'll get a different number. And I should get a different number because I'm going to be in a different row, a different column, and a different light value. So I move it up there, and I get a whole different value. When I compare them, you can see that you can check out for your own grid what each pixel looks like. And while we're here, I want you to take a look at this background. See all this beautiful background here? Why is it salt and pepper? Are you telling me that there's a little bit more light here than there is here? A lot more than there is here? And a little bit less here? No. This should be all a uniform gray if the world were perfect and there was no randomness in it. But in fact, there's a randomness, and that randomness is called noise, because these should pretty much be the same value all the way. All those stars should pretty much be there, or all those dark areas should be pretty much the same value. But obviously they aren't. That's why they're coming out salt and pepper like that. So here's that star. When you take that star, you get shapes like this, and you get all these different values across. And that's what it actually looks like if you were to map out the values. You can see that there's something going on in the middle here because the numbers are bigger. But there's some other things that you might want to check out while you're here. One is, you notice how this is an 8 up here, 14? Most of these are 14s across here. See all the 14s? That's pretty much the black sky. The black sky out there is pretty much 14s. The bright stars, pretty much 255, 256. There's a few exceptions. Here's a weirdness. We're going to have to talk about that weirdness later. Here's a weirdness. Right in the middle of all these 14s, there's a 256. How's that happen? I don't know. But up here, there's an 8, 10, 12, and then it starts in the 14s, runs across, and then it gets back down to the 8s, 8s, 8s. And look at this whole little corner is a little bit dimmer. The numbers are a little bit smaller. Over here, the same thing. All right, you're looking at vignetting, and you find that in most optical systems. There's just a little less light in the corner, and so it's showing up a little less. So remember when I said that it's all numbers? It's all numbers, and this is how they're stored. In your Fitz file or your TIFF file, you've got a indicator right here, and it says 2615. That means there's going to be 26 elements across and 15 elements down. It says 14 down there, but you got to count the 0 also. And so the first 26 numbers, all the way down to where? Here, I think, all go in the first row. And then when you're finished with that, just keep putting them into the rows as you go along. And that's what a Fitz file will look like. And it's a little more complicated than that because there are comment sections of it and various other things. But that's generally what it looks like. And before we go on, I don't believe there are any questions. I'm kind of monitoring. I remind everybody that if you have any questions as we go along, to go ahead and type them into the chat over on theastroimagingchannel.com. If you're, for some reason, over in YouTube and making comments over there, please understand that we don't monitor that, so we won't be able to answer it. But I don't see that there's any questions so far, but that's good. That means that everybody's gotten everything so far. Let's look at some of the things that can happen on a exposure. Here's 2 exposures, the same exposure. Here's a third one up here. I want you to notice something. See these 3 stars? Those 3 little dots of light? On every single exposure with my little camera, you're going to see that. It's just a fact of life. Sorry about it. It's a fact of life. You're going to see that little problem, okay? And that's called a hot pixel. My electronics are such that for some reason that always reports out brighter than it really should report out. There's some other things that you can see. Let me see, what's my list here? Okay, there's some cold pixels also. All right, this whole column here. See this thin column over here? A little bit more stretched over here so you can see a little bit better. That whole column just doesn't report properly. It reports with a little bit less than it's supposed to, and so it comes out looking black when I stretch it out. There's cosmic ray strike. See this cosmic ray strike? Boom, dot, dot, dot. On no other exposure will you see that, because it happened just once. It happened in a split second when something hit the sensor, and the sensor can't tell whether it's good light from the stars or good light from the nebula or just something hitting it randomly from outer space. And so it says, hey, I just got hit, so I'll register some electrons and let you deal with them later. There's also random noise, and we talked about that. That's why some of these little dots out here are brighter than other dots. That's why we get a salt and pepper effect instead of a consistent single gray color all the way through there. So these are all things that can go wrong, and I'm going to categorize them as random quantum fluctuations. These are just things that happen with quantums. There's some randomness to it. There's random one-time events like this cosmic ray strike. There's consistent electronic events like these hot pixels and these cold pixels. They'll always happen on every exposure with this particular camera. And then there's consistent optical events. To illustrate them, remember earlier I was talking about vignetting. Nearly all cameras will have less number up in the top. They'll have smaller ADU numbers up in the corners like this. And anybody who's had dust on their filters, that dust will block a little bit of the light coming in, and so it's going to look a little different. This vignetting and these dust bunnies are consistent optical events. They cause outliers, they cause errors, and what we're going to do with statistics is we're going to get rid of them. Somehow or another, we're going to figure out how to get rid of all those uglinesses, all those aberrations, what we call outliers. The way we do that is that we don't have a grid, we have a matrix. This is just one sub-exposure, this one right here. Here's another one, here's another one, here's another one, here's another one. So we got 5. In a good night, we'll take 20, 30, 50 of these suckers, and we'll have for the location 1, 1, it's a 10 here, and actually it's a 10 in all these because this is just copies of the same thing over and over again. But in real life, that might be a 10, and it'd be 11 here, and a 12 here, and a 10 here, and a 10 here, or something like that. So for each location, for each pixel, we'll have a matrix, and what we're going to want to do is dive down through that matrix and grab the various pixels values for each of those things as we go along. And that's what this looks like. Now, you saw the matrices. This is not the same grid that we had before. This is running along one of these rows over and over again. This is in a one sub-exposure, the next sub-exposure, the next sub-exposure, all the way down. So we've got like 8 sub-exposures sitting here. And you can see that the numbers are not the same. First time we took the picture, we had a 14 there, then a 15, then a 12, and etc., all the way down. Now, this is called variance. It's the difference between one and the other. And when you get a pile of numbers, they're going to vary in real life, okay? And the job of our statistics is to get rid of that variance and find out what the real centers of that information is. For instance, if you get a 14, a 15, and all the way down to this 14, you can average it in various ways. The 3 most common are a mean, which means that you add up all the numbers and you divide by the number of numbers. This is the average that we're taught when we're in 8th grade. You just add the numbers and divide them, and you can see that, yeah, all those numbers average out to about 14. But there are other averages out there. One of them's a median. And what you do with the median, you see these numbers here? Okay? Rank them. Rank them from the bottom to the top. And then take the middle of them, and that's your median. And it can be argued that the median is actually a better average than the mean. Same thing for the mode. This is, you rank them again, and then you realize that, hey, there's more 14s in that than anything else. So 14 is probably the accurate number. So you can do that over and over again. You get the mean, the median, and the mode. So you've got 3 different averages. And you know what? They're going to be different. They're going to be different because of the methodology they use to pick them. And that difference may mean something when you're processing an image. We're going to finish just a little bit another section here, and I see that Mark has a question over there. We'll go back over to that. When you go into PixInsight, you get your choice of how to integrate the image. and you can integrate it according to average, which is what I call the mean, median, minimum, maximum. They don't have one for mode, and that's understandable. So you know, you get your choice of which ones you want to do here, and there are reasons you might want to pick one and reasons why you might want to pick another. But before we go into those reasons, let's talk about some things that could really upset the apple works here. Actually, let's go into Mark's question here. Does anybody know if noise from the sensor is normally distributed? What is the probability density function of the noise? That sounds like a David question.
Yeah, so there are multiple sources of noise inherent in CCTVs and CMOS sensors. The sum total of them tends to be fairly Gaussian in distribution. So it's more like a normal distribution. Some of the sources, like dark noise, tends to have a slightly more salt and pepper-like effect. But once you average all those things together, it tends to be more like a normal distribution. So we treat it like it is Gaussian in nature.
Yeah, and Gaussian just means that it's got a normal bell curve, and we're going to look at bell curves in a little bit, okay? Look at these people. They were all told that if you wanted to be in this ad, you all had to get your teeth whitened. Now, one of these guys has a cousin who's a dentist, and he's got some negatives of him back in the days when they took negatives, doing some weird stuff, so he got it done for free. That was nice, wasn't it? Now, another guy had cancer of the jaw, so before they whitened his teeth, they had to make teeth for him and all that other stuff. So he had to pay $100,000 in order to get his teeth whitened. Some of the people, you know, they just went to their dentist and they got whatever it is. Now, what is the actual cost of getting your teeth whitened? Well, the mean cost with this bunch is $14,333. The median is $4,200, and the mode is $4,000. That's a little bit of different, but it's significantly different if we just take the mean, because look at this big ugly thing up here. Look what it's doing to the average. These are called outliers. The 0 and the 100,000 are outliers. And part of what we're doing with astroimage processing, part of what we're doing is that we are trying to figure out how to get rid of outliers. So let's talk about that. Or as Linda says, yes, the median will reject outlying data better than the mean. You know, I should have a slide like that coming up pretty soon here. Is that Linda? Yeah. So these are the outliers, all the weird stuff. We talked about them. We know what they are. What if we were to get rid of this guy and get rid of this guy? All right, just X them out. Don't worry about what their numbers were. Now we find out that our three numbers have gone, hey, they're pretty similar now. Okay, instead of being $14,000 for up here, hey, look, it's a much more sensible. It's going to cost me, you know, $4,000 plus to get my teeth whitened now. All right. So how do you get rid of the outliers? There are various ways, but it's called pixel rejection. That's what you do in astroimaging. You reject pixels, and you can reject pixels in any one of a number of ways. And we aren't going to talk about all of the ways that we can choose which numbers to ignore. Linda just pointed out one where she said, hey, the MinMax is better for excluding, and it certainly is, and we'll get to that. But as you can see over here, you can get percentile clipping, sigma clipping, Windsorized clipping, average sigma, and it goes on like that. And these things can matter to you. Much of the time they don't. You can be pretty happy if you've got a sufficient number with Windsorized sigma clipping, but we'll get to that. Clipping, by the way, means clip, clip. You just get rid of the outlying edges and you deal with the rest of the data. MinMax, you exclude the highest and the lowest. There's no analysis going on. It's very good for rejection. However, you may be rejecting good data. What if this guy here actually only paid $5,100? You know, he didn't have cancer of the jaw. All right, he only paid $5,100. You know, it might have been nice to be able to use his number in the first place. So you got to be careful with MinMax. Maybe you don't want to reject it. There's a second method called percentile rejection. And from what I've read, there's two different ways of thinking about this percentile rejection. Of course, you rank them from the lowest, you have the whole range from the minimum to the maximum. And then the first way is to take the median and exclude anything that's more than anything, like 10% from the median. So if the median is 4,200, anything that's less than 4,200 minus 420 or more than 4,200 plus 420 doesn't get included. So you're left with these figures here, and you average them out. Or a different way of thinking about percentile rejection is that you can reject, the top 10% and the bottom 5%, or the top 10% and the bottom 5%. It may work out to the same thing if you've only got these 8 samples, but if you've got lots and lots and lots more samples, you may be doing yourself some good doing it that way. Okay. Sigma clipping is a little bit different. Sigma clipping relies on you finding what the average difference is between one piece of data and another, between one exposure and another. Oh, I didn't clean up that slide. It shouldn't be out there. You shouldn't be out there. Get away from there. Okay. So the first thing you have to do is you have to determine the distribution of the data. And you get whatever that is. And then you reject anything more than a certain number of standard deviations, and that's called sigma, or sigma, from the Greek sigma, from the mean. And this is good only if you've got more than 8 or 10 images, because you can't really figure out a good standard deviation until you do. Going down here, you ask, what's a standard deviation? Well, remember when, who was it, Thomas or Mark? Asked about normal distribution. This is normal distribution. It peaks in the middle and it falls off evenly to either side in an even tail. Okay, the even tails on both sides. And while you're at it, you can tell if you've got a perfectly random distribution that 34% of the samples will be lower than the median and 34% will be higher. So within one standard deviation, plus or minus, you get 68% of the samples. In 2 standard deviations, you get 95, and in 3 standard deviations, you get 99.7. The average IQ, by definition, is 100, and the standard deviation is a little off of 15. So between 85 and 115, that's where you will find 68% of the population. Between 2 standard deviations, which is 70, and 130, whoops, sorry about that, you will find 95% of the population. And as you go up from there, you get more, okay? This is what it can look like sometimes, all right? This is noisy data down in here. This is not so noisy data, although this isn't astroimaging data because it would have more natural, this incidentally is called the bell curve because it's shaped like a bell. All right, so if anybody throws the word bell curve around, there it is for you. How do you work out a standard deviation? Well, you don't. You tell the software to work it out. It's pretty smart at doing that. But if you want to know what it's doing, and by the way, there are various ways to get this, but for our purposes, you take a value and you add all the values together and you subtract by the number of values and you get 241. That's a standard mean, okay, just like we talked about before. And then you take the value and you subtract the mean from it, and you get a number. By the way, these are all rounded off, so don't expect 3 squared to be 11. It's actually 240.75 or something like that, and it goes from there. And I should have caught that before, but I didn't notice it till later. Look at, sometimes they're below, sometimes they're above, but all squares are positive by definition. When you multiply a number by a number, whether it's positive or negative, you get a positive number. As long as both of them are either positive or negative. At any rate, your total number of deviations squared is 1,336. You take the square root of that, and then you kind of average it. You take the square root of the number minus 1, and so that's 5. So your standard deviation is 5. So most of your readings will be at 240 in this case, but they'll run from 239 to 245, someplace in there. That's where most of your readings will run. The more samples you've got, the more this helps, this works out for you. That's what a standard deviation is. Now, what you might be asking, you've seen Windsorized clipping, Windsorized sigma clipping. What you do is you rank everything, just like you have before, and then you take anything that's below a certain percentile or above a certain percentile, and you say that it is at that percentile. For instance, that 0 is below the 5 percentile, but hey, you know what? I'm going to put it at 4,000. And this one up here, this 100,000 is way above 5,000, but I'm just going to call it 5,000. This means that you can still use that data point as a data point, but you've substituted a more realistic figure for it. Yeah, it was brighter, but it's not nearly 100,000. You got to assume that. And that's what the Windsorized does. It's not very complicated. I thought it had a big mystical thing going on, but no, it's not all that tricky. Okay, that's Windsorized, but you need a lot of subs in order to get that to work. By the way, I don't mean to be PixInsight centric here, but if you're using the wrong integration method, the wrong averaging method, or then the wrong clipping method, it'll tell you. It says, hey, you don't have enough subs for that. You can use it if you want, but it's not going to give a good result because the mathematics just aren't there behind it. How are we doing on questions, everybody? I think we're having an argument about how many subs it takes to get a good, to use one of these versus another one. How are we doing, guys?
David's, I'm just reading it. David's saying you'll get different answers for how many samples you need.
But from different fields, David, do you mean from different, like in electronics versus imaging versus sound?
Yeah,
analysis?
if you take a straight statistics class versus, you're taking an astronomy class, you're going to get different answers for how many samples you need to determine standard deviation or a good mean, right? So if you're doing something in medical, it's completely different, right? So, Yeah.
I guess it's more than that. There is a slide to that effect a little bit later. Everything you hear here is, remember, is one guy who took statistics a long time ago and has been working with astroimaging for a while. It is not, except for when David speaks, somebody who actually knows statistics and uses them in his daily life a lot, okay? So far, these are the kinds of things we talked about. And I'm showing PixInsight here, but we've talked about how you integrate the image and which method you can choose and why you might want to choose one or the other. And we've talked about pixel rejection. We've defined some of the common terms of statistics and why you need to know some of these things in order to make sense out of making these decisions over here. We've talked about what outliers are and how to get rid of them through pixel rejection, and we've talked about those integration algorithms. So I did think that there is a number that keeps coming up for us over and over again that we quote, and I'm not sure that everybody has a common understanding of what this is. Let's take a look at our PhD graph here. All right, we can see that we want it to be at 0. We want it to be solid steady right across that 0 line and not go up and not go down. That means that we're tracking perfectly. That's what this one is right here. See how this is tracking perfectly? There's no ups and there's no downs. See how this one is tracking really weird? By the way, I did have an actual PhD graph with this exact pattern to it, but it's on a computer that died not too long ago, and so I can't get it to you. But there's a couple of definitions I want to go through here. These two have the same average error. This one and this one has the same average error. But I did want to also define what peak to peak means because that came up on cloudy nights the other day. Which is it better to have, good RMS or good peak to peak? And the answer is it's good to have good both, low RMS and a very low peak to peak. But peak to peak simply means from the top of one error to the bottom of the other error. So this is a peak to peak from 0 to 2, all the way down to -2. From +2 to -2 is a peak to peak error of 4. Okay, and that's not good to have a peak to peak error of 4. However, if your aberration is like, there's not up here. I should have thought of this, put it in here. If you had one start here and it came all the way down here and then came up here and all the rest of this over here were pretty much even, wouldn't be a big deal. All right, because it can sometimes have variations as long as most of the time it's on that 0 line. And the way you tell if it's on the 0 line most of the time is with a low RMS. Now, I said earlier that these two actually have the same average error. That's because the average error here is 0 plus 0 plus 0 plus 0 plus 0 divided by 18 is 0. So that's an average error, a mean error of 0. This one is +2, -2, +2, -2. You add all 18 of the pluses and all 9 of the pluses and all 9 of the minuses together, or whatever that is, and you get 0. And you divide by 18 and you get 0. So it's got the same average. That doesn't do us any good though, because it's an ugly line and we wouldn't want that as our graph. So if you define your error as mean error, that's what you would get. Instead, let's define it as an RMS when this is a set of readings. It's not a it's not a PhD readings, but the mean is 240.75. And if we subtract the actual ADU that we got from the mean, we get 3.25, 15.25, 28.75, and all that down. And then we square this, we get 10.56, et cetera, all the way down. And then we add them together. And then we take the average of that number. I'm sorry. And then we take the square root of that number. We're going to get a number that tells us, in general, how far away we were from that line. And it's called RMS. Now, particularly here, realize that RMS measures many things in science. And you don't necessarily have to have an ADU minus a mean. You can get an RMS from just one particular set of numbers, and it'll for instance, if you have AC power, you've got a plus number and a minus number, a plus number and a minus number going back and forth 60 times a second. When you add up the total and do the RMS number on that, you actually get the direct current voltage from that. So in different fields, RMS means slightly different things, but it all depends on this very same thing here, where you square the numbers and then you take the total, find the average of that number, and then find the square root of that, okay? So that's what an RMS is, and you want the lowest. And this is the slide that I was talking about was going to come up eventually. Different applications use different formulae. Some applications use expected or computed values, where I've described the average values, and it goes on like that. Okay, got it? Let's see, what do we do question-wise? Where are we with questions?
I think David's kind of been answering the more complex questions in chat as we go.
Yeah, I think Mark was asking that, if the mean was off, then sigma clipping would be off, right? And the answer to that is yes. And that's why we use things like Winsorized clipping, which handle outliers in their calculation, right? So that you toss the outliers before you're doing the mean calculation, as an iterative process, so that you get a more accurate mean before you actually reject things. Right.
Okay. Dithering. Dithering, he said. Look, this is the same star field taken in 4 different frames. You notice that ugly hot pixel? Here it's off the edge of a star. Here it's completely off the star. Here it's way off the star, and here it's back on the star in a different location than it was here. That's because I dithered. Remember, I told you these hot pixels, they're coming because I got a defect in the camera someplace. All right? But if I move my stars around, that hot pixel is going to show up in a different place. This is how we can apply the statistical advantages. So take my see it in location 13.6. Man, I got a black pixel there. In 13.6, I've got a black pixel. 13.6, same. Every one of those 13.6s is going to have a bad pixel. But look, in this one, it's in the third one down and the fourth one over. And in this one, it's the third one down and the fifth one over. And in this one, it's the second one down and the sixth over, or something like that. So the bad part of the pixel is in a different part of my star each time. So why don't I, after moving it around like that, go ahead and, if I were to just align them, if I were to not do any aligning on the actual stars, I would have at 13.6, I would have that bad pixel. And it would be consistently in that gray pixel that I had in all these subframes would still be there. But what if I take this star image here and instead align it according to where the star is? Look what's happened. These are the locations where those bad pixels were. All right? So for those of you who are wondering, why dither? Okay, why would you dither? Well, you dither because you can put the bad parts of the part that needs rejection, you can put them in different parts of the image so that they don't have nearly the power to affect the rest of the image. There's another thing you can do, a second application called Cosmetic Correction. Look at this, is that same star. Remember that star? And this was that bright one, okay? And what I can do is I can make a filter that says this pixel, this pixel, this pixel, this, and get the values for each of those pixels. This value is 150, that one's 40, that's 40. This one's a 140, 100. And that one's 256. It's way too bright. And so what I do is I go and I look at each pixel. And if there is a pixel that is way too bright, however I defined it, I say stop. I want you to average all of the values around that pixel and put it there for that pixel. That's the effect of basically saying, hey, you know that person with the $100,000 teeth whitening job? No, the rest of these people only spend about $4,000 or $5,000. So average out what they did and put that on that person right there. And that's called cosmetic correction in PixInsight, and it's got other names in other pieces of software. A third way to get rid of those outliers and use them to your advantage statistically is dark frame subtraction. Remember I told you that those three would always have those errors there. And look, my dark, it's got those same errors there. What if I subtract this value from the equivalent in each one of my subs? I just basically take that overpowered pixel completely out of the picture. Okay, it's not completely out of the picture because the chances of this matching exactly what that value is a little off, but that is what dark frame subtraction does. Okay, it subtracts all the hot pixels that it sees here from any hot pixels it sees up there, and thereby pretty much removes most of the dark pixels. Now, in fact, it's a little more complicated than that. It doesn't just flat out subtract them, it does some averaging and some stuff like that sometimes. But it is basically a subtraction process. Flat frame division, another way to correct the outliers. You take the flat exposure, and you know that if it's a flat exposure from here to here, it should be the same value all the way across. You determine the average of all of the pixels in the image, and you decide that that average is what the pixel is supposed to be. That's called normalize. And now you're going to normalize. You're going to adjust the overall values of each of these pixels so that they are all comparable. Then you take a look at each pixel and determine what part it is of the normalized value that it should have. And then you divide each of the subframes pixels by the result of that. In other words, if this pixel is half as bright as the average of all pixels, its ratio, let's call it, is 0.5. It's half as bright, so its ratio is going to be 0.5. If you divide the value of the pixels in your light frames by that 0.5, dividing by 0.5 actually doubles the ADU there, and it's now 2 times what it was. That's what flat frame division does for your images, to throw out the outliers and correct them so that you get a better, it corrects the outliers back to a normal, what it should have been in the first place. Now, I should say that 0.5 would be rather extreme. This is what a flat frame looks like unstretched from the camera. It's basically gray to the naked eye. You can't really tell that it's all that different. It's only after it's stretched. This pixel that we're talking about may have been 95% as bright as the pixel next to it. And so when you've established its ratio, you actually multiply the dark frame or the light frame by 1.052 or so. So it's not nearly as dramatic. I mean, your flat frames won't look like this when they come out of the camera. They'll look like this, and it'll be hard to tell the difference. It's only after you stretched it that you noticed it. Well, there are lots of statistics. I think I've covered the ones that you're going to run into most. Just remember that it's not just art and it's not just science, but a lot of what we're doing every day is statistics. All right, and that pretty much is the presentation. Now let's go back to the questions, I guess.
Thanks, Alex. One of the questions, and again, David answered it pretty well. So dithering takes time. For short sub exposures, you might get significantly less time imaging. In that case, should you dither after each sub, after every other sub, 1 in 5 subs? Is there a sweet spot for dithering depending on sub exposure time? And as David answered, there could be a lot of different answers, basically depending on your own equipment, settling time in particular, download time, exposure time. Even what's popping into my head is if you're shooting with a mono camera and you're flipping between subs, excuse me, and you're flipping between filters, you may find that you don't need to dither until at least after that third filter, the RGB dither. But it all depends on how you set up your gear, how you set up your software. But a lot of the software does have options for that type of thing.
Yeah, I'll add one thing to that, Adam, which is that for my own stuff, I just generally try to keep whatever the total download plus dithering plus focusing, whatever else is going on that isn't actually imaging time. I try to keep that to about 1/10 of the total time that I'm spending imaging, right? So I will try to tune my exposure times and stuff like that so that they're long enough that those things are having less of an impact, right?
Mm-hmm.
So it's still a balancing act, and it's going to be highly variant upon what you're doing. But if you're taking short exposures, then yes, you're probably going to want to dither every 3 frames, 5 frames, 10 frames, right? Depending on how short your exposures are, how fast your downloading times are, things like that.
Right. But if you're taking short exposures, the assumption is you're going to have a lot of them.
Yeah.
So then there really isn't a need to dither after each individual exposure.
Right.
You're still accomplishing the same thing by doing it. And then somebody said, what is it? The rule Zach follows is dithering after every 0.05 times the number of frames. So the more subs you have, the more subs you have, the less frequent you have to dither.
There are guys with mounts, there are ladies with mounts that take them 15, 20 seconds to settle after a dither. Maybe you need to dither less frequently. There are those that it takes 3 seconds, 5 seconds to dither and settle. Go for it. You can dither every time if you want. There are those who are out doing narrowband imaging and you've got half-hour exposures. If it takes you a significant amount of time to dither, in a half-hour exposure, you got to really work on that mount. There's something wrong. So it all depends on what you're getting the most out of. The important thing is that you've got to move those bad pixels around in relation to the defective pixels. Yeah, to the star. I'm sorry, to the star and the target.
Awesome.
I think CJ had a question in the room, right?
I didn't even notice that, but yes. So which is better, dithering or darks, or a combination of both?
I don't see why anybody has to choose between those.
No, do both.
Yeah.
Every time. Yeah, the only reason why you might not do darks is if you have a non-regulated camera, meaning there's no temperature regulation. So DSLRs and things like that. But even then, you kind of want to do darks with bias and do dark scaling, right? So even then, you still want to have darks in some form, but.
Yeah, because I've heard in a few different chat rooms that if you're dithering, there's no purpose in doing your darks, but I've always done both. So I was just curious though if one really is more significant than the other on that.
Yeah, if you're not doing darks, you're just relying on statistics to try to correct all of the defects in the sensor, and it's easier to just fix the defects in the sensor up front as much as you can, and then rely on the dithering to fix other things that are normally going on, the really bad pixels and stuff like that.
Let's look at this picture right here, this slide. You notice that these are still grayish. You know, where they should be white, they're still grayish. So if you had actually done a dark frame subtraction and stuff like that, or cosmetic correction, because dark frame subtraction wouldn't do much for that dark frame. It'd do something for this gray one down here, but not much for that black one. But at any rate, I just don't understand why people don't choose to do both. So it would reject as many outliers as you reasonably can before you do your statistics.
Well, I think as David pointed out, with a camera that doesn't have regulated cooling, that would be a reason to not use dark calibration for astrophotography. But I can't think of any reason why not to dither. I mean, I guess if your mount can't do it well, that would be a reason. But basically, just moving those pixels that slight little bit is gonna work so much of the first hot pixels, but also like that, as Mike Witt is pointing out, like the walking noise. The walking noise, in a sense, is a non-random dither, right?
Yeah, I think you know, there are guys that say, "Hey, I've got my mount is so bad at auto dithers, where you know, it's moving enough on its own. Why should I tell it to move?" Well, yeah, and I think you'll see the pattern.
Yeah, that's a non-random dither, which basically is a bad dither, right? But that walking noise, so the walking noise, you see it, right? So that noise is in there. The only problem with it walking is that it's not random. If that was randomed out, it would be working the noise out of the image itself and appropriately dithering.
Yeah, the walking effect is usually from, you know, a differential flexure or something like that, right, where you're guiding and there's some sort of mechanical movement between your optical systems. So you get a constant drift or polar misalignment or something like that. And the noise that you're seeing creating that walking noise is typically from hot pixels, right? So, you know, doing dark subtraction up front can help reduce the walking noise, and then dithering on top of that can really, really kill it.
Linda points out something very important here. There's so many people that ask, how should I do this? How should I do that? It really, you go figure. I mean, do some testing. That's what Mooney nights are for. that's what, there's a whole lot of situations where you can actually go out and you can check this stuff out and see how it works. And see whether it works for you, or if it doesn't. You may have a camera that has so little noise that darks don't really help you. Power to you, you know. But for most of us, it almost always makes a difference. So, Linda, it's good to point that out.
And at least at that point, whatever experience you have, whether it works or it doesn't work, if someone says, well, why do you do that? You could say, well, I tried it both ways, and this one seemed to work better for me. So you can speak from experience. And you're always, I feel like you always learn better by doing, not just by trusting what someone said.
Yeah.
Okay. I don't see any other questions. It was a great session. Dare I say statistics can be fun, but I don't know. I think statistics are kind of fun in astrophotography. You know, we like the pictures we take, but even Alex, he's a little bit of a gearhead, and we like to know what's going on inside of our cameras, and particularly on kind of the statistical side of our cameras. So I don't know, that was a cool presentation. I like presentations like this. Thanks again, Alex.
You're welcome. You're welcome. My pleasure.
And guys, remember, submit for images of the week. I don't have anything yet for next week, but I will try and come up with something and post it midweek. I have a few things that I think are going to be lined up in the future. So just keep your eyes on our website, where we hope to post them in advance. That said, again, thanks for coming, and good night.
Good night.